Hey class, here we are in Unit 9, and we're going to learn about probably the most important part from Unit 9, and that is how to do linear algebra using NumPy. So we saw before that NumPy works in arrays, and an example of an array would be a two-dimensional array, which is like a matrix. So let's just see a few convenient ways to create a two-dimensional array that might match how we would think about writing down a matrix. So the most obvious way to create a two-dimensional array or a matrix in NumPy is to just write it out and explicitly set the values. So we can write out a matrix in sort of a row format by using a nested list. So this is not yet a NumPy array here. This is a Python list, but then we can convert it into a NumPy array using the np.array command. So we have an opening bracket, and then we're going to have a list of rows. So the first row of this matrix will be 4, 3. Then the second row will be 6, 2. Okay, so you can see uh, to begin with, after doing this, it's still a Python list of lists. Then we convert it into a NumPy array by saying np.array. And notice that it becomes a 2 by 2, and it's printed out like we would expect, that the first row is 4, 3, and the second row is 6, 2. Notice that when I print it as a NumPy array, it prints it like a matrix, whereas when I print it earlier up here, it's a Python list of lists. Okay, so it's kind of a two-step process. Step 1, create a nested list or a list of lists in Python. Then step 2, call the NumPy array command and it will convert it into the matrix or two-dimensional array shape. Sometimes we want to use backslashes to allow us to specify Python over multiple lines. Okay, so you can do this like this. So here I'm specifying my array, and it looks like, I think I don't even need those backslashes. I don't think that I need those. Let me just take a look. When I made these lecture notes back in the day, things are a little different with Python. Yeah, you don't even need the backslashes. They're optional, but you know what? Let's just get rid of it. You can use multiple lines in Python to specify your list. So, modern Python, no problemo. You can just write out the matrix on multiple lines. No problem. So what I'm showing you here, just to make sure it's all clear, is that you can just basically write out on multiple lines your array and then convert, or sorry, your list and then convert it to a NumPy array. Why would you want to do this? Maybe because, you just want to be able to quickly look and say, okay, yes, this is the matrix 4, 3, 1, 2, minus 1, 4, 4, 2. Maybe it's more visible too. You might, you can even line it up, right? So Python doesn't care about spaces. So you could maybe line it up a little bit more. So, now it really is clear. You could even align these things. There we go. Now that is a clean looking matrix. Cool. So there you go, multiple line matrix. Just like when we were making arrays with NumPy, you can create an array and then set the elements using slicing. So here I create a matrix that is a 2 by 10 of zeros, so it's 2 rows, 10 columns. Here I printed it out. And then I can just maybe make column 1, so this is column 0, then column 1 be equal to 2. I can make row 0 equal to minus 1. So I'm saying for every column, but specifically row 0, make it minus 1. And then I can set a specific element, so row 1, column 6, make it 43. And I could do even something more sophisticated like making a loop. So this is showing you one kind of interesting trick, is that if you call numpy.shape on an array, it gives you the number of dimensions for each, the number of elements in each dimension of the array. So because our array is 2 dimensions, right? Because it's a matrix, so it's a 2-dimensional array. there are two sizes. Well, the first is the number of rows, and then the second is the number of columns. So this is a quick way to get out the number of rows and columns of a matrix. Okay, and then what I'm doing here is I just did sort of a for loop over the columns and made them all equal to powers of 2. So the first column only in row 1. So row 1, column 0 is 0 squared, row 1, column 1 is 1 squared, row 1, column 2 is 2 squared, rows 1, column 3 is 3 squared, etc. So, these are just 4 examples of how you can explicitly initialize different parts of the matrix. Okay, so that's a lot about how to, make your matrix. Okay, so we saw explicit initialization, and then we can also construct it by using for loops or, slicing out rows. We didn't see this in this example. We've seen previously that we can use numpy.1s instead of numpy.0s. We can use numpy.random to make random matrices. So there's a lot of options there to make the matrix. So once you have your matrix defined, we want to do some linear algebra. There's a number of linear algebra routines that you can do. We can take a look, why not? You can do Cholesky decomposition, QR decomposition, singular value decomposition. You can do eigenvalues, eigenvectors, which we'll see. You can do norms. You can do logarithmic determinants. You can do traces. You can do least squares. You can do inverses. You can do Penrose inverses or pseudo inverses. You can do tensor inverses of arbitrary dimensions. So a lot of options there. Okay, but we'll just see the main ones. So obviously the first thing you're going to want to do if you have two matrices is to compute a matrix product. So we know there is the asterisk in Python, and that is for an element-wise product. Okay, so that is not the same thing as matrix multiplication. Remember, matrix multiplication is like, the row times the column, and then you sum. If you do asterisks, that means multiply each element in matrix A by each element in matrix B. So the two matrices need to be the exact same size, which is not true of matrix multiplication. Dot is how we do matrix multiplication. Okay? So here I make two matrices, a 2x4 and a 4x1. In these, I use the random numpy command to make the matrices. Then I compute matrix 1 dot matrix 2, and this is the result of matrix multiplication. So you see we have a 2x4 and a 4x1. So these dimensions cancel out, you can think of it. So the result is a 2x1. Okay. Now, in newer versions of Python, I think starting at 3.7, we have the at character, and this special at character replaces matrix multiplication. So rather than needing to do the dot, 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 we can just use the ampersand. So then you can just do, this multiplied by this is matrix multiplication using the ampersand. Sorry, not ampersand, the at symbol. The at symbol. So I think in general, you can just basically use this everywhere. It's been maybe a year and a half or 2 years since 3.7 came out, so most of you should have Python 3.7 installed. I just wanted to, just in case, some people have older versions of Python, but I think this is pretty common now where you can safely just always use the at sign when you want to do matrix multiplication. And notice this is for NumPy arrays. I don't think this works for lists in Python. This is not a Python thing. This is only for NumPy arrays that you can do this matrix multiplication. Like I said, so the asterisk, right, it's element by element multiplication. So it only works if the two arrays are the same or the two matrices are the same. So here, remember that matrix 1 is a 2x4 and matrix 2 is a 4x1. So you could not do element by element multiplication because they're different shapes. Okay, so if you want to do matrix multiplication, don't use asterisk. That's element by element multiplication or element-wise multiplication. Use the at symbol. So this is just sort of a small point. Um, you can use the matrix, then period dot, the other matrix, or you can use numpy dot dot and put in both matrices. They are equivalent. They're just, this one is an example of a method, this one is an example of a function. You don't need to pay attention to this because you can just use the @ symbol. I just want you to know that there are two ways you can do this, so just in case you see it somewhere else in NumPy, it's the same thing. Okay, it's the same thing. All right, so now we know how to multiply matrices. A pretty important thing is matrix rank. Okay, so you can compute matrix rank using the matrix rank command. So this is the first example of using the linalg command. Did they remove this? I didn't see it in here. No, it's still there. Good. So you can import numpy.linalg as linalg. This is just a shortcut so I don't have to type out numpy.linalg. Then linalg.matrix rank gives me the rank of the matrix. So here is an example of 1, 0, 0, 0. So for those of you who are taking linear algebra right now, you should recognize that the rank of this matrix is only 1, right? Because this is a scalar product of this, because you multiply this row by 0, you get this row. So the matrix rank is only 1. So there you go. Matrix rank correctly gives us a 1. And then sort of the next thing you might learn in linear algebra is how to compute an inverse. So an inverse is important for solving systems of equations. So consider this system of equation: 3x plus 2y plus z equals 5, 2x minus y equals 4, x plus y minus 2z equals 12. We can rewrite this in matrix form. So here I've written this out where I have the matrix of coefficients. So in the three equations, we multiply a 3, a 2, and a 1 by x, so a 3, a 2, and a 1. Then we have a 2, a minus 1, and a 1 for the y. And we have a 1 and a 0, and then a minus 2 for the z. Then I put down the variable column. So this times this should equal 5, then this times this should equal 4, this times this should equal 12. So I can rewrite this using single letters indicating these matrices as ax equals b. Then if I can find the matrix inverse of A, I just need to multiply it by B, my scalar column here, to get X to solve for all three variables simultaneously. So let's see how we can do this in Python. I'm going to go and remove those backslashes so I don't forget. Great, that's fine. So I can define my A matrix using explicit initialization. Then I can define my B matrix. Okay, now one trick here is that remember that in here, B is a column matrix, right? It has three rows, one column. If I define this in Python here as this list, I have to sort of transpose it, right? So then here, when I create the A matrix, that's fine. It was defined in row major form, row, then row, then row. But for B, I defined it as kind of like a column all at once. So I have to call, all right, I can call transpose here. Like I could have made these individual lists, but it's just maybe a little bit easier just to put transpose there. Okay, so this little bit of code here turns them into matrices in NumPy. Then to compute the inverse, all we do is call linalg.imv. Okay. Now maybe in your class, your linear algebra class, you guys are by hand computing matrix inverses. Maybe you guys are learning, what is it, like reduced row echelon form, doing Gaussian elimination. I can confidently say you will never use that in your life. Okay, like there has been one time I used Gaussian elimination in my life, and I do a lot of math, compared to the average person, and it was not with numbers. It was like in some bizarre algebra system. So it was totally off the wall, random use case. You will always use a computer to invert matrices. Okay, like it just I don't trust you. You shouldn't trust yourself. No one should trust anyone to do a matrix inverse. We will always use computers to do that because it's confusing. It's just a lot of arithmetic. I mean, that's why computers were invented, was to compute matrix inverses. Okay, there you go. One line of code. You can compute the inverse of a square matrix using linalg.imv. Okay, this computes the inverse. This solves the problem. Remember, we still have to multiply the inverse times b to solve the problem. As long as we're editing the lecture, let's just go and replace it with an at because I think it looks nicer. Where to put all my code here? We will use an at because it looks pretty. Beautiful. Okay, so then this solves the problem. Now, down here, I just want to make sure it's the correct solution. So if it's the correct solution, uh, then a times x should equal b if I have the correct x. So I multiply my a times the x I found, and I get out 5, 4, 12. So indeed, my x vector of 2.47, 0.94, and minus 4.3 solves the equation. All right, so that's a matrix inverse. All of this code I just showed you, it is all just setting up the problem. Um, there's only one line of code you actually need to know to compute a matrix inverse. All of the other code was just to motivate why you would want a matrix inverse. All right. Now, one of the funny things about matrix inverses is that they're very expensive. They scale, I think, by the fourth power of the number of, no, maybe it's this, yeah, the fourth power of the number of elements in a matrix. So computers are very fast, though. Computers can do billions of operations per second. So you can do pretty big matrices, but I would say maybe 500 by 500, maybe 1,000 by 1,000. That's probably the biggest matrix inverse you can compute. Now you may be thinking, Professor White, why would I ever need to solve a 1,000 by 1,000 matrix inverse? There are situations when you need to solve them. Maybe I can think of, a handful of times when I needed a matrix inverse bigger than 500 by 500. It comes up sometimes. And part of the reason it comes up a lot is because a lot of engineering problems these days have a lot of data. And matrix inverses are a common transformation we do on data to solve specific problems. So it can happen. So just think if you're doing a matrix inverse, if it's 1,000 by 1,000, probably not going to be feasible. But if it's less than that, you could probably compute it. You might need to wait a few minutes if it's over 500 by 500, but that's sort of the upper limit. Okay. So eigenvectors, eigenvalues. The actual Python to compute eigenvalues and eigenvectors is again one line. I'm going to attempt to teach you a little bit, just a little bit of intuition about eigenvalues and eigenvectors. The only reason I am going to attempt to do this is that it took me a long time to learn what eigenvalues and eigenvectors were. I don't think it was really until maybe I was a postdoc, so postdoc is what you do after you get a PhD, that I really feel like I understood it. So I think any time you can learn more about it is always good. But there's probably some video on Khan Academy that explains it brilliantly, and I could have just watched it a long time ago. But in any case, I will try to give you guys an appreciation for eigenvalues and eigenvectors from a very different perspective than what you're probably learning in your class. Okay, and my way of showing it is going to be from an analogous problem. So you guys probably won't take a class on this, but if you do ever take a class on Hilbert spaces or linear operator theory, I highly recommend it. Beautiful class, and it teaches you this sort of divine connection between functions and matrices. So it turns out that if you make matrices infinitely dimensional, like you make the matrices bigger and bigger and bigger, you make them infinitely dimensional, they are analogous to operators. And operators are things which transform functions. So, a function takes in a value, gives you a value. An operator takes in a function, gives you a function. And infinite dimensional linear algebra is operator theory. Okay, so beautiful stuff. It's mind blowing. Just great stuff. So this is an analogy like that. Okay, so functions, matrices, brilliant connection. Anyway, but let's take a look at eigenvalues and eigenvectors of functions. So the analogous operation to eigenvalues and eigenvectors is finding a stationary point of a function. Okay, so we're no longer in matrices, we're now in functions. So a stationary point is where the input and output of a function are identical. That is, if you give an x argument to f of x, it will give you back x. These are really important. Okay, so let me give you a motivating example. Let's just say I have a function. So I'm making up this function. Okay, I'm calling my function, it's x minus the quantity x squared minus 612 divided by 2x. Just that's a function. I'm just telling you that's a function. Let's say I found the stationary point. I found the point where the input and the output are the same. That would mean that x is equal to x minus x squared minus 612 divided by 2x. Now, if you do a little bit of algebra, you can show that if x were to satisfy this expression, then x squared would equal 612. Okay? That means I'm finding the square root of 612. Okay, so finding a square, if anybody's ever tried to compute the square root of 612, you may have been like, wow, how do you compute the square root of 612? Like one idea would be to do a Taylor series expansion, which hopefully you've learned in calculus. But this solution method was that what you're looking at here, this function here was invented by Isaac Newton, and it's a very elegant way to solve a square root. Okay, so it turns out that this function is a very special function. That is, if you change what a is, and you find the stationary point, it allows you to compute the square root of an arbitrary number. Okay, so there you go. I just said, if you can find a stationary point, you've solved square roots, and you can in fact construct this argument for any algebraic expression. So any number or any algebraic expression you wanted to compute, like the square root of 612, or maybe you wanted to compute the log of the sine of the tangent of x, you can turn them into these stationary point finding algorithms. And that's how your calculator computes square roots. That's how your calculator computes, inverse tangents. So this is how computers compute these things, is with stationary point finding. Okay. Now you may be wondering, okay, yes, you've converted it to finding a stationary point, but actually how do you find the stationary point? Well, it's not really relevant for our argument. Like a stationary point I'm going to tell you is analogous to an eigenvalue eigenvector, but I can just tell you a fun, easy way to find stationary points is you just do this. You compute f of x, and that's your new guess for x. Then you compute f of that x, that's your new guess for x. Then you compute f of that x, and it's your new guess for x. And it turns out this process just eventually becomes stationary. Wow, right? Wow. Okay, so here you go, computing the square root of x. You could just use a for loop. Okay, I'm just showing you a for loop. You don't really need to look at the code, but basically I guess that x is 1. So I guessed that the square root of 612 is 1. It's a bad guess, right? You should know it's a bad guess. But it turns out just following this process where I compute f of x, and I make that my new guess. Okay, so I start with 1. That's my first guess. Okay. And then it turns out, okay, 1 was bad. My algorithm says 306. Maybe that's better. Okay, it turns out that's bad too. Then 154, then 79, then 43, 28, 25, 24.74, 24.73, 24.73, 24.73. So this, you need to do basically 5 steps of arithmetic to get a very good calculation of what the square root of 612 is. Okay, so that whole argument was just to show you that stationary points are things where the input and the output are the same, and it's a really important technique in numerical analysis. Analogously, eigenvectors are where you find an input and an output that are the same for a matrix A. Okay, now let me go back a little bit here. Think about this, is that this point x that's stationary, that's a property of f of x. Like it's a property of the function. For my function, there is one stationary point. Turns out there's 2 stationary points for square roots, right? Minus 24, but ignore that. Okay, so there is something intrinsic about A, my matrix A. There is some intrinsic input which is going to be equal to its output. Okay, so that's what an eigenvalue eigenvector is. You put in x here, and then it gives you the same output. And that's where I kind of view A as a function. Like it is some kind of a function whose input is x and output is y. So think about A as a function. It takes in an x and outputs a y. And an eigenvector is a vector where if I put it into A, I get it back out. Okay? Now there is one caveat here. There's one caveat, is that we allow the flexibility that there can be a scalar here. Okay, so it's going to be only the direction that's preserved. So when we talk about eigenvalues and eigenvectors, the eigenvector v that goes into A, we get the same vector out, but it's scaled by one number. And we call that number that scales it the eigenvalue. Okay, so this is a property of A. So A is my matrix. And for my matrix, there exists a vector where when I put it into A, I get back out the same vector in it, but it's scaled by the scalar called my eigenvalue. Now, just like I said, for the square root example, there are two stationary points. Okay, one of them was, minus 24.7, one of them is positive 24.7. Just, square roots have two things. And along the same lines, for a particular matrix A, there are multiple eigenvectors, and thus there are correspondingly multiple eigenvalues. And the number of eigenvectors you get out is equal to the matrix rank of A. Okay, so this whole discussion here is to give you an idea of what is the eigenvector of a matrix. The eigenvector of a matrix is a vector such that when you have A operate on it, where you operate just means A is multiplied by the vector V, you get back out the same vector scaled by a little bit. Okay? All right, and why is it important? Just like we saw with square root, there are certain numerical problems where finding the eigenvector actually solves something for us. What's the most famous example of why eigenvectors are useful? The most important, fundamental, most fabulous, most accurate, most wonderful theorem in the world is the Schrodinger equation. Quantum mechanics is probably the most tested and outstanding theorem ever devised in physics. Accurate to ridiculous precision. Whereas you go look at, Einstein's theory of gravity, and there's still some problems with it. Whereas quantum mechanics, man, that has got it down, perfect. Anyway, in quantum mechanics, like the solution of the Schrodinger equation is one of the ways to solve it is with eigenvectors and eigenvalues. So great example of why it's useful. Okay, so all that discussion, what is the actual Python code? You just literally call linalg.eig. There are two variations. One of them is called EIGH, and this is for Hermitian matrices. We're not going to go really into too much detail, but basically EIGH will guarantee that you get real numbers out. If you use EIG, you can get out complex numbers. And that's just one of these things about matrix eigenvalues, eigenvectors. We always are guaranteed to get as many eigenvectors as the rank of the matrix, but some of them may be complex. If your matrix is Hermitian, you get real eigenvalues. So Hermitian, basically a symmetric positive definite is a Hermitian matrix. Just basically means that it has a rank equal to its, it's a square. It's being symmetric proves it's Hermitian, and then it basically has a positive determinant. I don't think it needs to be symmetric. It just needs to have a positive determinant and have full rank. Okay, so let's take a look at some examples. We'll go into a little bit more about Hermitian versus non-Hermitian. So let's take a look at this matrix A. It's a 3, 1, 1, 3. And we're going to try to pretend like it converts, we'll think about it as operating on two-dimensional vectors, right? So I said for our analogy, we put a vector into the matrix, we get out the same vector. So imagine you're putting in a two-dimensional vector into 3, 1, 1, 3, and then we get out another vector. Okay? So let's try a vector like the vector 1, 0. Now, if I multiply A times 1, 0, okay, so I take 3, 1, 1, 3, and multiply it by 1, 0, I get out a 3, 1, okay? Now, is this the same direction as 1, 0? No, it's not the same direction, right? Like, if you imagine the vector, here it is as 1, 0, so that means it's moving 1 on the x. And then when I multiply it, it becomes 3, 1. So it's like, maybe like this, okay? So this did not preserve the direction. Now, if I compute EIG, okay, so here I enter in my array, and then I call EIG. EIG gives me two things, the eigenvalues and then the eigenvectors. Now remember, there are multiple eigenvalues and eigenvectors. So for a 2 by 2 matrix, we should get 2 eigenvalues and 2 eigenvectors. So the eigenvalues, you get two numbers, 4 and 2. The eigenvectors, it appears as a 2 by 2 matrix. And each column are the vectors. So the first vector it finds is 0.7, and the second one is minus 0.7. So let's see, indeed, are these directions preserved? So if I multiply A, my 3, 1, 1, 3, by 0.7, I get 2.8, 2.8. And indeed, that is the same direction. It was originally, 0.7, and then it became 2.8, 2.8. So the direction is the same, and it was scaled by 4, right? It was multiplied by 4. Okay, and just put that, get rid of that dot. I don't like that dot in there. I just want to use at symbols as much as possible. All right, so you can repeat this example with a 0.7 minus 0.7 or minus 0.7. You'll see that indeed the direction is preserved. Okay, so let's talk a little bit about Hermitian versus non-Hermitian. If you just make a random matrix, you just pop some numbers out of your head, it will typically be non-Hermitian. So you will have complex eigenvalues and eigenvectors. But if you look at any matrix that arises from an engineering problem, 99% of the time it's Hermitian. So if you're like solving ODEs using matrix analysis, it will be Hermitian. If you're solving, a system of mass balance equations, it should be Hermitian. If you're doing energy balance, it should be Hermitian. It's just most problems in nature kind of obey this positive definite requirement so that it has Hermitian matrices. Okay, so what does this mean, for you? It means that if you're doing any kind of homework problems, you should probably use EIGH. And the reason why is that sometimes, just due to rounding errors, you will be left over with tiny little, this is a bad example here. I don't want to see that example again. If you were to like enter in your homework problems and then into a matrix and then solve the matrix using EIG, not EIGH, EIG, you sometimes can have leftover little complex parts. Like you might do it and you might see, oh, okay, there's like a 0.008 here, right? And so just to get rid of any complex component, you can use EIGH instead of EIG to remove that small complex amount. So, but, you know, it's not wrong to use EIG, but sometimes you just want to be like, yes, I know my problem is an engineering problem. Yes, I know it should come out to have no complex eigenvectors, so I will use EIGH. Okay. You're never wrong to use EIG. It's never really wrong. Just sometimes it can be a little bit annoying to have tiny little extra complex numbers added to your eigenvalues and eigenvectors. This kind of comes down to the fact that the way Python solves linear algebra problems is to do a lot of numeric methods, right? It does numerical methods. So because of, as we learned previously, due to rounding error and floating point precision losses, you can end up with tiny little imperfections that can lead to complex numbers. And here I'm just showing you that if you just make a random matrix and you call EIG, you will have some little bit of complex numbers here because random matrices are generally non-Hermitian. So EIG works everywhere. EIG is never the wrong answer, but sometimes in engineering, you want to use EIGH just to remove any small complex values. Yeah, I don't think I ever covered this, but just so you know here, in Python, you can do complex numbers. So like here is my complex number. Instead of using I, it uses J. Excuse me, why J? Because in physics, people use J in math, I forget. Some discipline uses J instead of I. Physics does a lot of weird things like that to be cool. It's probably physics using J's. In physics, they also do the integral, they do the integral, and then they do the variable of integration. So they do like the integral dx, then they do the integrand. So like integral dx sine of x. Why? I don't know, man. It's physics. They want to be cool. I mean, to be fair, physics probably invented integration, and physics probably invented complex numbers before mathematicians did. That's kind of how a lot of this stuff works out. But they just like to be different over there. Anyway, so you can do complex numbers in Python if you use EIG. G, they will arise. If you use EIGH, you're telling Python, yes, my matrix is Hermitian. Please do not have any complex component to my eigenvalues and eigenvectors. Okay, so, there's not really a lot for me to teach about linear algebra. You should learn the concepts from linear algebra in your class. What this lecture does is sort of equips you in how to get a matrix into NumPy, how to multiply matrices, how to work with them a little bit, and then basically you look in the linalg library to find any matrix algorithms, decompositions, computations you want to do. And I think you'll find that you can do almost anything in Python that you would do in your linear algebra courses and quite quickly and efficiently. So hopefully this lecture helps you out in your other courses, and we'll just see a little bit of linear algebra in the rest of this class. This lecture is more preparing you for your junior and senior level courses where you'll be doing eigenvalues and eigenvectors a little bit more frequently. All right.